This is a video for AQA Further Pure Mathematics, Matrices section 5.3, where we're finding eigenvectors and eigenvalues for 2x2 matrices. We've seen in previous videos how the characteristic equation, which is the determinant of m minus lambda I, is found. And we're going to now use that characteristic equation to look at a 2x2 matrix to find its eigenvectors and eigenvalues. The characteristic equation tells us that m minus lambda I, the determinant of that, must be equal to 0. So taking the matrix M and then simply subtracting lambda on the leading diagonal produces this equation. The determinant we find in the usual way, so that means that we have 2 minus lambda multiplied by 5 minus lambda and then minus negative 2 must be equal to 0. And that we can multiply out to give the quadratic, which is lambda squared minus 7 lambda plus 12 is equal to 0. This factorizes to give lambda minus 3 and lambda minus 4 equal to 0, in which case lambda is equal to 3 and 4. So we can say that the eigenvectors have these eigenvalues (3 and 4). So now that we've got these eigenvalues, we know from the definition of an eigenvector that m multiplied by v is lambda v, where lambda is the eigenvalue, and therefore we can write that as m minus lambda I times v is equal to 0. So looking at our original matrix, if we subtract lambda from the elements, then we can write that multiplied by the vector xy must be equal to a 0 vector. Now the matrix comes from different values of lambda, so when lambda is equal to 3, that's our first eigenvalue, then the matrix is 2 minus 3, which is negative 1, 2, and then negative 1, and 5 minus 3, which is 2. So that's just substituting lambda equal to 3 into this matrix here. Now if we multiply out the left hand side, you can see that we get minus x plus 2y in both cases. So therefore we have that minus x plus 2y must be equal to 0. So this is the invariant line, and that has a vector which is 2, 1. So that vector 2, 1 in the direction of the invariant line is an eigenvector, or any multiple of that. Similarly, if lambda is equal to 4, so this time we're subtracting 4 from the matrix, we get negative 2, 2, negative 1, and 1 multiplied by xy must be equal to 0 vector. And this time we get minus 2x plus 2y, or minus x plus y, equal to 0. So both of those are equivalent to minus x plus y is equal to 0. So this is the invariant line, and that is the same as y equals x, which has a direction of the vector 1, 1. So 1, 1, or any multiple of that, is the other eigenvector. So to find the eigenvectors, we take each of the eigenvalues in turn and substitute them into the equation m minus lambda I times v, a general vector, or the vector that we're trying to find for the eigenvector. and that must give us the 0 vector. So we end up with two invariant lines, and the vectors in the direction of those lines are the eigenvectors. So here we have a picture of what's going on here then. We've got the matrix, which we're considering 2, 2, negative 1, 5. And each of the eigenvectors are marked on there. 1, 1 and 2, 1. Now if we look at what happens to each of those vectors, the green one first of all becomes the vector 4, 4. So that point 1, 1 has mapped onto the point 4, 4. Similarly, 2, 1 has mapped onto 6, 3. So that the points have moved by the value of their corresponding eigenvalues. So this one here has moved by 4, and this one by 3. So the lines may be invariant, but points are not invariant. They end up at different points but on the same line. Of course, they would be invariant points if we had a special case where lambda was equal to 1. Well, that's the end of this video looking at 2 by 2 matrices and eigenvectors and eigenvalues. And in the next one we'll look at what happens when we've got 3 by 3 matrices.